So the first thing we're going to review here, we're going to go all the way back to the very beginning when we first talked about limits. So when you're taking a limit, you'll either be approaching a constant. It could be 0, could be 5, could be pi. Remember that when we're approaching and we don't have any little plus or minus superscript, it means we're coming in from both directions. And as we approach a constant, we always first plug it in. Rarely does that work, but if we get a number, that's our answer. Although that's not generally going to be the case. Usually what's going to happen is we're going to get an indeterminate form, and that usually is of the form 0 over 0 or infinity over infinity. So for AP, and again, this is just strictly AP review, so there's a lot more to this that we've covered, but I'm kind of streamlining it towards test prep. So remember, the biggest tool we have is to factor, cancel. Remember what that does when we factor and cancel graphically? It means there was an undefined y value at that constant, but when we come in from both directions, we're still arriving at that y value. So we cancel, factor cancel, and replug to arrive at the limit. The value, y value there doesn't exist, but the limit does. Part B, there was some other stuff we did, like multiplying by a conjugate if we see the roots. We had our trig stuff, but honestly, if it goes to those, you're going to learn something called L'Hopital's rule this semester. So I'm just going to put L'Hopital's rule, and this we will be waiting on until we cover it. This kind of is a tool that'll take care of all that other stuff we did when we got 0 over 0. If we get a number over 0, like say our limit as we approached 5 of the function equals 7 over 0. What that means is we didn't get cancellation, and it means we have a vertical asymptote at 5. So we have to decide if we end up heading towards infinity or negative infinity, or if it's a two-sided limit, which means we are not, again, if we're just approaching from the right on an asymptote, we can only go up or go down. It's either this guy or this guy. But if we're approaching from both directions, sometimes we get, that split personality going on, and then we say we have a true D and E. So remember, to figure out which ones it is, we become a creeper. The one that gets a little tricky, and it still seems to throughout the years cause problems, is the absolute value issue. So let's go take a look at what happens when we take the limit as x approaches, let's just say 2, of the absolute value of x minus 2 over x minus 2. What happens with that is, because the top of the function, the absolute value function, and I'm going to again repeat the actual formal definition of the absolute value function, is that it equals plus or minus x, depending on whether you're coming in from the right or the left. So what happens when we get this absolute value over, let's do even just this one, is that the top is plus or minus x and the bottom's x. What that means is we get a plus or minus 1. Graphically, what happens is, as long as x is positive, 7, 8, 9 will be up at 1. But when x goes negative, maybe negative 5, we'd have the absolute value of negative 5 over negative 5. We end up at negative 1. This graph is always what happens in this scenario. The only thing that might change is where that discontinuity lives. So this is still going to be plus or minus 1. The difference is the boundary is at 2. So anything bigger than 2, like a 4, will cause it to be 1. Anything less than 2, like say a negative 4, you'll notice on that we'd get a 6 on the top and a negative 6 on the bottom. So that's the general graph of the absolute value. So watch this. If I come in from the right, the answer to this is 1. If I come in from the left, the answer is -1. If there is no one-sided approach, the answer does not exist, or the limit does not exist. So next up, we could also be taking limits as we approach the infinities. Remember, that's all about, we're going on out and we have to consider what happens when x gets incredibly large in magnitude, be it to the right or to the left. We look at the highest degree of the polynomials, and if the highest degree is on the bottom, then our limit is 0, because that bottom is going to get huge compared to the top. It's going to approach 0. If the highest degree is on the top, then our answer is plus or minus infinity. And again, to determine which, we have to do some sign analysis. If the highest degree is tied, then we use the coefficients of the highest term. So I'm just going to put HP for highest power. Keep in mind that these actually provide us with the horizontal asymptotes of the graph. If my limit as x approaches infinity of a function is equal to 2, really what it means is that I have a horizontal asymptote at y equals 2. So these provide us with the horizontal asymptotes. Let's move right along here. So let's go do a couple examples. A limited x exists if and only if the limit as x approaches a from the right of whatever function you're working with equals the limit as x approaches a from the left of the function. It need not be continuous, because remember, we can arrive there and the function cannot exist there, but this y value is our limit. We are sitting there. So usually all we need to do when we're finding the limit as x approaches -4, notice I'm not approaching 0. This is find the limit as x approaches -4. So that means I use this and I just plug a -4 in. I get 16 minus 4. My answer is 12. However, if I were to ask you, what is the limit as x approaches 0? Remember, without a plus or a minus superscript, this means that I'm approaching from both directions. So I put a 0 in here, and I'm at -4. And remember, though, this is interesting because this right here means I'm approaching from the left. No, it doesn't. Sorry. I thought that this said does not equal. So what I do here, if I'm coming in from the left, I simply put in a 0 and I'm down at -4. Graphically, it looks like this. Open dot here, everywhere to the left it's the parabola, but everywhere to the right of 0 it's this line. So if I'm approaching 0 from the left, my answer would be -4. If I'm approaching 0 from the right, my answer would be 3. But if I say from both directions due to a lack of superscript, my answer would be does not exist. That was our first topic of the year in 8 minutes. Moving on to our next topic on continuity. There's a 3-part definition to continuity that you need to be comfortable with. So a function is continuous, let's say at x equals, let's use c, if and only if. First of all, f of c must exist or must be defined. There must be a solid dot there, otherwise I'll have to lift my pencil to hop over the hole in the graph. Also, the limit as x approaches c from the right on the function has to match up with the limit as x approaches c from the left of the function. What that means is not only do I have to have a solid dot there, but I can't be sitting there like this where I'm defined at c, but my limits are different. That is not a continuous function. And lastly, whatever that limit might be as I come in from c from both directions has to actually match up with the dot that exists at c. And again, if you're going, oh, I know all this, that's awesome. It means your retention is great. But what I'm trying to do is sort of pick up people who maybe have forgotten and pick up some pieces here in this review week. Speaking of pieces, how about a piecewise function? When we're asked if a piecewise function is continuous, we really just need to make sure that these three things happen. And really the biggest one is this guy, that when we come in from the left, we're equal to where we come in from the right, because it's almost always going to be defined. So let's go take a look. Sorry, had to clear my throat. Right in your ear, right? So we've got a function defined as a rational expression, x squared minus 1 over x minus 1. That's when x doesn't equal 1. Understand what that means. This is from the left and from the right. So as I come in from the left, I'm at that function. As I come in from the right, I'm up at that function. At 1, I'm at 4. So just kind of keep that in mind. Now let's go talk about what the function looks like. If I were to factor this, my difference of squares, a lot of times if you have a good graphical interpretation, you won't have a graphing calculator, but it really helps if you understand what the graph looks like. It makes the question so much easier if you could get a visual. So I know that I actually have the line y equals x plus 1. The only difference between this guy and this guy is my original function does have a discontinuity at 1, which means there's a hole at 1. All right, so let's go see what the graph of that would look like. It'd be the line x plus 1 with a hole when x equals 1. That's what that top piece is telling me. Everywhere x does not equal 1, which means to the left and to the right. At 1, there's a dot at 4. This is obviously not continuous. It violates that third property that says the dot has to, oops, sorry, I was trying to drag that in. It says the dot has to fill the hole, and this one doesn't. It's up at 4. So let's go see. Does the limit exist? Yes, the limit's 2. I'm at 2. Does f of 1 exist? Yeah, f of 1 is 4. Are we continuous at 1? No, because we'd have to lift our pencil because we violate the third property that we wrote of continuity. So this would be C. Let's try another one. If x is continuous, so they're saying we have a continuous function here at 0. Everywhere x is not 0, that means to the right and to the left. Basically, you get the whole picture of the function except what's going on at 0. Remember what we do. When we put a 0 in, we get 0 over 0. That's not good. We want to factor to see what's going on with this function. My issue was at 0, so I know that's going to cancel off. This is actually another line. It's 1/2 x minus 1/2. Okay, I'm not going to go graph it though, but that's exactly what's happening. Now it says f of 0 equals k. Well, what I know is I have to make sure that whatever I set it equal to, it fills the hole that got created. So all I do is replug a 0 back in, and I get negative 1/2. Makes it nice. Like if I were to go up to this one and say, oh, no, this is a k, what better it be? Well, it better be up at 2 because that's where my line is. See? All makes sense. It's so super. Calculus is awesome. All right. Now I've got another triply piecewise function. What is it telling me? That the top is the function everywhere except at 1 and at 2. I would go factor that guy. 3x times x minus 1 over x minus 1 minus 2. Get a good idea what's going on here. We have a hole in the graph or a discontinuity at 1. It's a removable discontinuity. Question's probably going to be, does one of these remove it? Okay. And we also have a vertical asymptote, a non-removable infinite discontinuity at x equals 2. So let's talk about where we have continuity. First thing I'm going to do is put a 1 into the function and see if that negative 3 plugged up the hole. Let's go check that out. 1, 1. I'd get 3 over negative 1, which is negative 3, which means we've got continuity at 1, right? At 2, there's an asymptote, so it doesn't matter that f of 2 is equal to 4. right? It just means that if there was some function at 2 and we have this asymptote here, it just means it's sitting there with a dot right there, but the function isn't going through there. So let's talk about where we have continuity. There's continuity at 1, correct? Zero is not an issue. When I plug in a 0, I get a 0. This function sails through 0, 0. So it looks like we're continuous everywhere except at that vertical asymptote. Next up, the formal definition of the derivative as a limit. That's actually worth rewriting. The formal definition says the limit as x approaches h from both directions, right, of f of x plus h minus f of x over h, let's do it over here, is equal to the derivative of the function. It's the formal definition of the derivative. I think maybe it warrants one more time a graph. So just one last time. You don't need to draw this graph on your notes, but I like to show you what's going on here because sometimes when you see it the first time around, it doesn't make as much sense as when we do it later. I'm going to move over here h, so actually just watch this picture. I'm now going to be sitting at x plus h. I'm moving h to the right, so this would be x, f of x. This guy over here would be x plus h, f of x plus h. Remember, the tangent line is this guy. Its slope is the derivative. Right now, if I were to do the average rate of change, which would be f of x plus h, sorry, I forgot my parenthesis over here, be change in y, f of x plus h minus f of x over x plus h minus x. That would be the slope of that secant line, the average rate of change. You can see that they're quite off, but as I have h approach 0, which means this secant line is going to get squeezed closer and closer and closer and closer to the tangent line, they eventually have the exact same value. And so your task is not to do it, but to recognize it. So the key to this is usually seeing that h approaches 0, and then you see. So this would be f of x plus h minus f of x over h. So I can see that x is a 1. I can see that my function, I forgot to put f of x plus h. I can see that my function is raising x plus h to the 6th. So my function is f of x equals x to the 6th at x equals 1. So what's its derivative? This is the formal definition of the derivative, but my power rule, I know that's 6x to the 5th, and at 1, it's a 6. So you just have to figure out who's the function, and at what value am I evaluating it. So maybe that deserves another one. I wonder if I have one on the next page. I don't. So let's go take a look at the bottom there. I want to put another one of those on here. A lot of times these are tricky, so let's go through a tricky one on here. Limit h approaches 0 from both directions. Let's say sine of pi over 6 plus h minus 1/2 over h. This is definitely in the format for the formal definition of the derivative. My h is approaching 0. I've got f of x plus h minus f of x over h. The question is, what's the function? I can see that the function's always kind of what's embedded in here. That's embedded in sine. In here is embedded to the 6th power. So my function, my f of x, is sine. I can see that I'm doing it at x equals pi 6ths, and that's why there's a half here. Because remember, it's f of x plus h minus f of x, right? So there's a half sitting there. So this is the formal definition of the derivative of the sine function. Well, the derivative of sine is cosine. And I'm doing this at pi 6ths. So the answer to this would be cosine of pi over 6, root 3/2. If you need to rewatch that, that might be worth it. So nothing on here is a weakness for you guys. I do want to make sure you remember the formal definition for not the product rule, actually, you guys are awesome at that. Not the quotient rule either. We got our low D high minus high D low totally memorized. I'm looking for that chain rule. Must be on the next page. So let's go take a look at this guy. And I'm going to talk for, I think I'll quit at 25 minutes maybe. Or actually, I think I'll probably go to 30. Sorry, got to listen to me a long time. So this guy right here definitely would require the quotient rule. Blah, blah, blah. Struggling today here. All right. So we are going to launch into our quotient rule, y prime or dy dx. I actually like this Leibniz notation. You'll learn why a lot in Calc 2. But we do low d high minus high d low. Drop the power down one. Don't forget the derivative of the inside function or the derivative of the guts. Draw a line and square below. The task now becomes to clean this sucker up. So I have probably the best way to do this is root 1 minus x minus, let's go do a little cleanup here. I've got my 2 going with my half, my x going with my x. I still have the negative here, so that's going to become a plus. And then this would be 1 over square root 1 minus x squared, correct? So again, I'm just doing a little canceling, watching my signs. I now have a complex fraction. Complex fractions get cleaned up with a little crisscross applesauce. We always start in the top left, go down to the bottom right, we multiply. I think I forgot something. Is that an x squared or an x? It's an x squared. So I forgot the x squared on this guy. All right, so on the top I'd have a 1 minus x squared on my criss minus my cross all over multiply across, which would be 1 minus x squared radical, and then this guy, remember we collapse as a product. Looks like my 1's are gone. I end up with a negative x squared. I'm going to go look and see if, yeah, I can see I got a none of these going on here. So, no sense continuing, right? Let's go to the next one. Derivative of our trig functions, awesome. You should have those memorized. These two generally are not on the AP exam. I really do want to stress the chain rules formal notation. So remember, when we're taking a function of another function, like sine of 4x, and we are taking its derivative, so we're taking its derivative. Really what we do is the derivative of the outside function, that's what this is saying, f prime of, so this would be cosine of. We keep the guts intact, so I'd say 4x. So on here I'd say g of x times the derivative of the guts. So times 4. So the formal definition, really, really important. I believe on one of the FRQs that some of you guys had on the last test, it said f of, and then there was like an x squared minus 2x. And you were supposed to find the derivative. It might have even been phrased as the slope of the tangent line or whatever, but that would have been f prime. You don't know what f is. If it was sine, it goes to cosine. You leave the guts intact, and then you multiply by the derivative of the guts. These are often tabular or reading them off a graph, so they might say, what's f prime at, say, 2? And you go put a 2 in here, and anyway, you keep on working it. I'm going to skip this trig one. I think you guys are fine with the chain rule. Little review on motion, and then I'll quit. Remember, for particle motion, we've got position, sometimes called s of t or x of t. We've got velocity, and we have acceleration. And when we're working down the screen, velocity is the derivative of position, acceleration is the derivative of velocity or the second derivative of position. And when we integrate, we work back up. So very important that you can go both ways. So let's go take a look at this trig one. We've got s of t, I like that as a function. That means position. I'm being asked to find a model for velocity and acceleration. These are derivative questions because I'm working down my paper. So for velocity, this will be a product rule. I'll do first d second, the derivative of tangent is secant squared, plus second d first. And that would be done. And if I had to do it at pi over 2, I'd put in a pi over 2. But that one's done for velocity. First d second plus second d first. Acceleration would take the derivative of this. So I would do first d second. This is chain rule. My outer function is a squaring function. I do 2 secant t to the first times. So I'm doing first d second, but d second is the chain rule. I bring the 2 out front, knock the power down 1, which doesn't need to be there, times the derivative of secant, which is secant tangent. So that's first d second plus second d first would be 3t squared. I'm going to squeeze it in front. That right now is just the derivative of the first part. Then I would do product rule over here. First d second plus second d first, and the derivative of tangent is secant squared. And there might be some factoring and cleaning up you can do, like I can see I've got 3t squared, I've got 2 of these that I could combine, but for the most part the calculus is over. For integration there were some formulas, and I'll quit at the bottom of this page, that you need to be comfortable with using. Usually with these, you are usually given, I'm saying usually, the velocity function, or you can find it. Total distance traveled is a question about feet or miles or yards. You can see in the label that this is about position. So again, if I have velocity, I need to go back to position. Again, if this is in feet per second, I want to know my total distance traveled in feet. This is an integration problem. So I know I need to integrate my velocity, my feet per second, times seconds, that's the dt, right? From time 1 to time 2. But every time I go backwards, I want that to count on my odometer. So just because I, headed to school and then about, 2 miles in, I'm like, oh, forgot my book and I have to go back. I have traveled 2 miles. My displacement's 0, but my total distance traveled, is 4 miles. So I need absolute value bars. Displacement for this scenario is 0. I don't want to make my negatives positive. I want them to send me back home. Where am I? I'm 0 from where I started. So that's where we just integrate the velocity. Notice for both of these, it doesn't matter where I start, and some of you are having a little bit of issues like that. So if it says x of, say, 0 equals 5, and they ask you, maybe this goes then from 0 to 7, if they ask you what your total distance traveled is in the first 7 hours, that 5 doesn't matter. That's where I already am before I start. I'm sitting at the parking lot of a gas station 5 miles from my house, and then I want to chart my total distance traveled. All right? So same with what was I displaced over the next 7 hours. This has nothing to do with my displacement from that gas station. What that initial position does is it affects where I am at the end from my starting spot. So usually you're given like I'm just going to put an 8 here. I'm going to leave it formulaic. So usually they'll say, where are you? They'll give you this. I'm just going to put a dot here. And they'll ask you where you are at some other time. So what you need to do is you have to say, well, where am I starting? Maybe I'm already 5 miles in. Plus then I'm going to get displaced over the next time interval. They might say at 2 hours in, you're back 10 miles. Well, then this would be a negative 10, and then I'd integrate from 2 on up to wherever I'm going to go. I need that initial condition when I'm doing my final position. And again, I'm not putting absolute value bars on here because my position is affected when I go backwards. Correct? This is my final position. And if this was already starting 5 miles from my house, I do 5 plus this movement, this movement, this movement. All right, that's it for this set. It's at 30 minutes. Awesome. Have a good one.